Okay, so the next thing we're going to talk about, we've been talking about particle kinematics. Now we're just going to extend it to particle kinetics. And remember, kinematics is just describing the motions without dealing with the causes. So that's like relationships between position, velocity, and acceleration. And then kinetics is combining kinematics with the causes. So combining kinematics with mass and force. And there's one equation of motion for particle kinetics. And that's Newton's second law. I'll always abbreviate that N2L, Newton's second law. And it says that F net is equal to m times a center of mass the meanings of these are F net is the sum of all external forces on the chosen body. M is the mass of the chosen body. And ACOM is the acceleration of the center of mass of the chosen body. One thing to notice about this is this only works if you're measuring your vectors in an inertial coordinate system. So what are the requirements for an inertial coordinate system? There's two of them. The first one is that the origin cannot be accelerating. And the second one is that the coordinate axes can't be rotating. You know, the coordinate system can't be rotating. Bless you. Well, some examples of these. Why can't the origin be accelerating? Imagine somebody on an elevator. And let's say that the elevator is accelerating upwards. Okay, and this person's acceleration is being measured by the coordinate system represented by that camera. Okay, well, if there's no acceleration, then, you know, you could, so he's standing on a scale here, you know, that's measuring his weight. Measuring his, yeah, weight. If the elevator isn't accelerating, the force shown by that scale is just going to be mass times, you know, it's just going to be the weight of the person, mass times 9.81. If that elevator accelerates upwards, the scale is going to read a higher number, okay, while it's accelerating. But what does that camera measure as this person's acceleration? That, according to that camera, this person is still just at rest, right? And so we'd have a case where if you imagine that the downward force is just still the weight of the person, the upward force is higher than the person, right? So we have a net force that's acting up, but the camera says the acceleration is 0, and so Newton's second law doesn't appear to hold, okay? Are you with me on that? And why can't the coordinate system be rotating? Picture that training centrifuge thing that supposedly they use with astronauts. So this thing's moving around in a circular path. And imagine that you had a camera that was fixed to this arm. So as this person moves around, that camera is measuring the person's position, and then you can use that to calculate the velocity and acceleration. Well, this person, the idea of this is that there's a big centripetal force on this person, okay? That's where you get the big accelerations. But if you're measuring your accelerations with this camera that's rotating, again, that camera's just fixed right on the person. And to the camera operator, they don't know why the person's grimacing and losing consciousness and stuff. As far as that camera can see, that person's just sitting there. Well, if you measure the forces with load cells in the chair or whatever, you're getting these big forces on the chair that don't appear to match with what that camera is measuring. Okay, so in order to use Newton's second law, you have to be measuring these vectors in an inertial coordinate system. Newton's second law, everything in it says something about the chosen body. So obviously you have to be very careful about what your chosen body is. You have to be very specific about it. In simple problems, that's not hard, but in more complicated problems, sometimes that can get confusing. So obviously being clear about the chosen body being clear about what the chosen body is important. And so every time we use Newton's second law, we're going to draw a free body diagram. So here are my rules for free body diagrams. And I'm going to abbreviate these FBDs. So first, draw a closed outline of the chosen body. And in this picture, you're not going to include any external details, no external objects. And you're not going to include any internal details. The only purpose of this outline is to make the distinction between what's in and what's out, okay? It's like Mean Girls. No internal details. They don't care about the internal details. They just care about who's in and who's out. So like, for example, here's the grass. And here's some guy. Singing opera or something, he's got pants, shirt, all this stuff. But when you draw your free body diagram, the only stuff that matters, if your chosen body is the guy, you don't have to be an artiste, but you just have to make it clear where the boundary is for your chosen object. So that's your free body. That's a closed outline. Well, it's not closed, but it should be.
It's like a chalk outline.
It does. But this is the important stuff. So this is not a closed outline. So be sure that this is just a line that shows exactly what's in your chosen body and what's out of your chosen body. And if you can't draw a closed outline of it, then you haven't in your head imagined a defined object, okay? And, also don't do it. I don't know why I drew this guy like this. It's a ridiculous pose, but Also don't do this, because what does the ground have to do with it? Now you're sort of like, maybe you know what you're talking about and you're just drawing that for context. But now the question is like, well, what's the external load? Are we talking about external loads on the ground, on the top layer of ground from the next layer of ground, So all we want is just an outline that separates what's in from what's out. After you have this, include all the external loads acting on the chosen object. And now you can break this down into only two types of things. The first one is field forces. Those are forces where if you know the location of the object, you know the force. Those are always conservative forces. Gravity is the main one. We're always going to include the weight. Other ones can come up, though, like electrical and magnetic field forces. So electrical fields, magnetic fields. But for the most part, this is the one that is going to show up. And then once you've dealt with the field forces, probably just gravity, the only other way these forces can come up is contact between the surroundings and that boundary that you've drawn. Here's something maybe you've thought about, or maybe this was brought up in your physics class, but I said that Newton's second law deals with all the external forces acting on a chosen body. Why doesn't it deal with the internal forces on a chosen body? Like, those are still forces acting on it. And the reason for that is that everything that happens inside that boundary, all contact forces that happen inside that boundary, come in pairs, come in Newton's third law pairs, So like, what if every time you drew a free body diagram, you had to think about like, oh, okay, well, like blood's applying this force to this heart ventricle, and then like this cell is transporting this material or whatever, like problems would be a lot longer, you know what I mean? But you don't have to worry about that, because inside the boundary that now you've already specified that you're worried about this person, the blood applies a force to the ventricle, but the ventricle applies an equal and opposite force to the blood, and so on. And in other words, all the internal forces cancel each other. The only forces that don't cancel each other are forces applied by the field that the person is surrounded in. And think about the forces that like the ground is applying to the feet of this person. Okay, since that's at this boundary, the force applied to the feet by the ground goes into Newton's second law. But since we're at the boundary, the force that the feet apply to the ground, that doesn't go in Newton's second law. Okay, so only the boundary, only at the boundary are forces applied to our object that aren't canceled out in a Newton's third law pair. Okay. So,
I have a quick
yes.
So in terms of our free body diagram, when we draw it, we're only going to look for forces acting on our object, not the force of the object.
Correct. Yep, that's exactly right. Yeah, if you want to find the force that your body applies to something else, then you draw a free body diagram of that something else later. Yep, that's exactly right. A free body diagram only shows forces, external forces on that thing. All right, so in representing these forces, if the direction of the force is known, then draw an arrow in that direction. And label it with a scalar number or variable. Okay, so why do you only need a scalar to as a label for this? Because if you know the direction and you can draw that arrow, then the only variable that's unknown is the magnitude of that force vector. Okay, so this is a way to be clear to yourself about how many variables you're introducing into your equations. If the direction is unknown, draw little arrows in the directions of the coordinate axes. And label it with a vector or a vector variable. Okay, so for example, for this unknown direction thing, so say that you're isolating this car. Looks like the Jetsons car. You can do it like this. This is how I tend to do it. Or a lot of people do it like this. Okay. How do you know when you're done? So again, I mean, you've seen mainly simple free body diagrams, and in this class, I mean, compared to how they can get, you'll see mostly simple free body diagrams. But in very simple cases, it's sort of self-evident when you're done. But in more complicated cases where there's a lot going on, it's nice to have something to just ask yourself, like, have I done this? So how do you know when you're done? So you're going to represent the weight force. And any other field forces. I mean, you'd know from the problem if there's an electrical field or a magnetic field or whatever. And then represent the force at any spot where the surroundings touch the boundary. And once you've done those two things, like once you've put in the weight force, imagine going around the boundary and finding there's contact here, 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 and here, and you've dealt with all those, you're done. Okay, so for example, let's say that there's this mud and there's a pig stuck in the mud. And someone's trying to pull the pig out of the mud with a truck. And there's a dispute about the pig's ownership. So there's somebody here trying to keep the truck from getting the pig. And this truck has a helicopter on it. You know, and so on and so on. Oh, and there's a bird on the, there'd probably be some kind of bird on the pig. Yeah, it's like that bird from Up. Remember that movie? Okay. That bird's falling off, but okay, so the idea here is there's a lot going on, right? Can you agree on that? But let's say that we just want to isolate the pig. Okay, so here's the outline of the pig. That's supposed to be its curly tail. I don't know what pig's legs look like. That does not look like a pig outline, but that's fine. Well, despite the fact that there's all this stuff going on, all you have is a weight force. Let's say some kind of unknown force vector applied by the mud. There's a cable force from the cable connected to the truck. And there's a downward force applied by the bird. And now you've gone all the way around the boundary of the pig. You've dealt with every place that something is in contact with it, so you're done with the free body diagram. Okay. Anybody have any questions about that or what I'm even talking about? Okay, there's one thing I want to introduce. This is just a notation thing, but it'll come in handy more later on than now. So this is, I'm going to call this the double subscript notation. For force, and we're not talking about couples yet. We'll talk about that later, but I'm also going to say and couple vectors. And so in this notation, a force vector is always going to have two subscripts. So let's say this is force AB. And this means the force vector applied to body A by body B. And you have to be careful with this. Don't think of this as just, the force between body A and body B, you know. In fact, in this class, just never think of anything starting with okay? Just, you're glossing over something if you do that. Okay, so the force vector on body A by body B, not the force vector body A applies to body B. That's backwards, okay? Unfortunately, some people, half the people use this notation to mean this, and half of the people who use notation like this do mean the force A applies to B. And as long as you're using it consistently, either one is fine. As far as I can tell, it seems like physics people tend to use the opposite meaning of this, and engineering people tend to use this meaning. So I wish I could give you the one way that everybody does it so you could communicate clearly, but I can't because people do it differently. You always can do, if you want to be extra careful, you could write the force vector on A by B. And that's probably a good thing to do if you're in a, in an environment where people aren't necessarily going to use the same notation as you. But no matter what order you use this notation in this class, I want you to use the one I use. What's the benefit of that? The benefit is that Newton's third law gets very easy to represent. The force on A by B is just equal to negative force on B by A. Okay, so We're going to use this notation a lot more once we get to rigid bodies. But we're going to use it because Newton's third law happens so easily and nicely. Are you with me on Newton's third law? That's like about as concise a definition in Newton's third law as you can give. If you have two bodies that are in contact, the one body A applies to body B is opposite the one body B applies to body A. I do want you to notice something though. Only use this notation for vectors and vector components. So for example, let's go back to this pig. He's turning into a cat. Well, what are the forces that we had? Remember we had the weight force. And then we had a downward pushing force from the bird. We had a cable force this way. And then we had this unknown force vector applied by the mud. This one, since that's a force vector, okay, we'll represent this as force on the pig by the mud. The other ones, we won't use this notation because these variables that we're associating with those forces are not vectors. They're just scalars, okay? And they're just scalars because we know the directions of all these things. Are you with me on that? No? So when you're drawing your free body diagram, you're always, with every force, you're going to think, do I know the direction of this force or not? Some forces, you know the direction right off the bat, like cable forces, you always know the direction a cable force applies. It's always parallel to the cable, away from the body, always. And whenever you have a force with a known direction, the variable or value you're going to associate it with is just going to tell you how long it is. The direction you already know, so you don't have to calculate that, okay? And so this reaction force from the bird, the weight force, and the cable force, those are all known direction forces. And so these variables are not vectors. They're just telling you how far you go in that direction, okay? And so if you're using that double subscript notation, there's only one place in this that we can use it. That's where we had unknown direction force and we represented it with a vector variable. The problem is if you use it here, okay, and call this like force on the pig by the cable, okay, or let's say force on the pig by the truck, that's the cable connected to the truck. Okay, then you draw the truck, you know the direction of the force on that, you draw it this way, but you think that you had to switch the subscripts on that, which would end up giving you the opposite sign of what you need. So if you do that double subscript notation thing on variables, scalar variables that are associated with known directions, you're going to get your signs wrong. Okay? But if you're doing things just in the directions of coordinate axes, then you can use that notation. Okay, so I'm going to talk about, I guess, 4 forces. So these are 4 force types that we'll see all the time. Um, 3 of those have known directions. Those are, I'm going to separate it into pushing contact, pulling contact, that whether there's a cable involved or not, you can always think of it as being applied by a cable. And the third one is friction contact. And then there's going to be one force with a unknown direction. And that is just going to be the force applied to a body by a pin. You can also think of that as a hinge or a ball and socket joint. This would be if you're doing a problem in 2D, and a ball and socket would be if you're doing a problem in 3D. So now I just want to go through these 4 forces just one by one, talk about how to represent them. Yeah.
What about the weight force?
Yeah, weight force. I guess I'm assuming you remember that. But I tend to use 9.81, by the way. I don't know. I think it's 9.806. So it's kind of right on the border of what's worth using another digit and what's not. Okay, so the first one is pushing contact. And you can think of this as, so if you have a pure pushing contact, you're ignoring any friction. And the direction of this force is perpendicular to the surface of contact toward the chosen body. I mean, if you want to, so a pulling force is going to be away from the body. You can make sense out of that if you just think of wearing like a big puffy coat and what happens if someone pulls on you versus pushing on you to the coat, you know? Like if you, like the direction the coat goes is the direction of the force. If someone pushes your coat, it mushes in towards you. That's a force toward you, you know? If someone pulls on it, it goes away from you. That's the direction of the force. So for example, if you have two carts like this that are in contact, and you apply some force here, let's call this one A and this one B. A free body diagram of A looks like this. So you have the mass of A times 9.81 going down. And now that you've dealt with all the field forces, just go around the boundary looking for contact. There's a pushing force at the wheels. There's really pushing forces at both wheels, but for now, these are particles, so we don't have to be too concerned about where they're acting. So I'm going to write this as normal force acting on body A. And then there's a pushing force. And how did I get that direction? You know, the surface of contact is the ground. It's perpendicular to the ground toward the chosen body. So that's this. There's a pushing force on A from B. The surface of contact is vertical. So the direction has to be perpendicular to that, toward the chosen body. Give that a scalar name. And a free body diagram of B. There's the weight force of MB times G. There's a pushing force from the ground toward the chosen body. This one has the 500. And then there's a pushing force from A, perpendicular to that vertical surface, toward the chosen body. And the magnitude of this force, since this is the same contact force as this, that variable has to be the same. Those values have to be the same because of Newton's third law.
Like one of them has to be positive and one negative.
Well, that is true. I mean, so the directions have to be opposite, right? But anytime you're representing the directions with an arrow, so anytime you know the direction of a force, you represent the direction with an arrow and you know what that direction is, then the variables you associate it with is just a scalar variable. And those scalar variables are the same. Okay, so if this one's 50, this one's 50. The directions are just done by the arrows. Okay, yeah.
Are we just using one normal force?
I am, just because I'm sort of glossing over it. I mean, once we get to rigid bodies, yeah, you would have to do that as 2 or 4 if you're doing it in 3. For sure you would, but right now doing it as particles, I just sort of skip that. What?
Now are we assuming we're in static equilibrium?
We don't have to yet. We don't have to at all, actually. whether you're in static equilibrium or not, those contact forces are the same. Those R values are the same. Yeah, that's Newton's third law. It's hard to wrap your head around, but there are things that just seem so weird with that. Like you're telling me that like if a baseball player hits a baseball 500 feet, when that ball's in contact with the bat, the ball is applying the same force to the bat is to the ball. It doesn't seem right because you never see the baseball player fly 500 feet, you know. But the baseball player also has a large mass advantage over the ball, and the player is also the one wearing spiked shoes and standing on the earth, you know. So the baseball player has a lot of advantages. But yeah, remember playing Little League baseball? What happened when, oh no, you guys didn't play with wooden bats, right? No wooden bats. Well, when you played Little League baseball in the old days, back in my day, like you'd hit the ball and it would make a funny noise and your coach would sort of bang the bat and be like, yeah, there's a crack in there somewhere, you know, and then you'd throw away the bat, get a new one for $8 or something. But if you see a broken bat in pro baseball, it doesn't happen like that. It's not a funny noise and whatever. The bat just explodes and pieces go everywhere, you know? And that's because, to hit a ball 500 feet, you have to apply a big force to the ball. That means that ball is applying that same force to the bat. Okay, anyways, I'm over time. We'll just talk about the rest of it next time.